for convergence. The integral test for convergence. If f is positive, continuous, and decreasing for x greater than or equal to some number m is a positive integer greater than or equal to 1. If we let a sequence represent a function, okay, so we let our sequence, our nth term of our sequence represent a function of x, then the summation, the sum of the sequence or the series, and this integration are either both going to converge or both going to diverge. Okay, so to use this property, you want to first establish that the three conditions, that we have a positive function, a continuous function, and a decreasing function, are met before you can apply the integral test. The AP exam will test you and your understanding of this. Okay, so let's look at some examples that I have laid out here and show you how this test can be used. So here's our first ones. Confirm whether the integral test can be applied to this series. So again, the conditions are a function is positive, continuous, and decreasing. So the first thing you want to do is, this is a sub n, is you literally let, and you write this out, a sub n equal f of x, which is going to be, just replace the n's with x's. So that's what we're going to do. Okay? So then we go through the conditions here. So if this is my function f, the first condition, is it positive? So f of x is positive for x greater than or equal to 1. Okay, remember this number m, where m greater than x greater than or equal to m, where m is a positive integer greater than or equal to 1, so 1 is the lowest we can go here. Take a look, any number bigger than 1 or equal to 1, this will be positive, and so we're good to go. So the next one is it continuous? F of x is continuous for x greater than or equal to 1. The only time it would not be continuous is if I had a point of discontinuity, or a vertical asymptote or anything like that, and the vertical asymptotes are when the denominator is equal to 0, which is, this will never be equal to 0 in the real sense. There is no holes in the graph, there's no common factor that can reduce, so this is indeed a continuous function for x greater than 1. Okay, so the third one, okay, is to show that f is decreasing. So how might I be able to do that? Well, to show that this function is decreasing, I can then take its derivative and show that f is going to be decreasing when x is greater than or equal to 1. So that's what we do. So what is f of x? If I rewrite it as a product, then I'll have x times x squared plus 1 to the negative 1. And we can do the product rule here. So we have the first, we're going to do the derivative of the second, so it'll be this negative 2, and then times the derivative on the inside, which is a 2x. And then plus the second times the derivative of the first, which is 1. And then you have this, we can clean this all up and see what we have. And I'm going to save us some time in all the simplifications of this. So you take a look at it, make sure you can simplify this out, so you can then make a judgment call on whether or not it's going to be positive or negative. And I have this right here over x squared plus 1 quantity squared. Okay, so if f prime of x equals this, then I can see from here, for when x is greater than 1, the bottom here will always be positive, but the top, because of that minus sign here, is always going to be negative. So I can then conclude here, so f prime of x is less than 0 for x's that are greater than or equal to 1. Okay, which means f of x is decreasing on x greater than or equal to 1. So does the integral test apply here? Can I use it for this thing? And the answer is yes. So since all three conditions are satisfied, we can apply the integral test. And I put an extra R in there that doesn't belong. Test. So there you go. Okay, that's how you got to set it all up. Here's another example. We do the same process again. So we have a sub n, which is going to become f of x, which is going to be x over the square root of 2x minus 5. Now, we need to find that this is going to be positive. Is there a number that will guarantee this thing to be positive for every x after that? That's what we're looking for. So f of x is positive. Okay, for what? Well, this right here is 0 at 5 over 2, or 2.5. Okay, but we don't want a 0 here. But so we know then, if I put a 3 in here, an integer, because remember the number has to be an integer, a positive integer, so no fractions allowed or anything like that. So if I put 3 in here, knowing that 2.5 is the 0, so the next integer up is 3, this will be always positive, that will be positive, so this is all positive when x is greater than or equal to 3. And that's how you get that number right there. So is this function continuous? When x is greater than or equal to 3? Well, the point of discontinuity, or the undefined part, is when this thing right here is 0, which will be at 5 over 2, which is below 3, so we're good here. So it's continuous. Okay? So the last one is to determine whether or not this thing is negative. Okay? So we want to find its derivative. And you can do it however you want to do it. If I bring it up here as x, 2x minus 5 to the negative 1/2, if I do it that way, I can do the product rule. So I'm going to have the first, derivative of the second, lower the power by 1, times the derivative of the inside, and then the second to the negative 1/2 times the derivative of the first, which is 1. So there's my derivative right there. I'm going to clean it up. Again, you practice this to make sure you can get to this answer right here. This is what I ended up with, and let me know if I have it incorrect, but this is what I have right here. This is 3 over 2. And so, when is this thing going to be negative? Okay. F prime of x is less than 0 for when? Okay. Well, if I plug in a 3, the bottom here will be positive, but 3 up here will make it negative, so it's going to be negative for that. And what about numbers in between? At 5, this will be 0. Anything more than 5, this right here is going to be positive. So nothing bigger than 5. Down here, less than 3, that 2.5 makes it a 0. We can't have that. So what we're looking at here is this will be negative when x is between 3 and 5. That's a good place to look at that. But what do we know? But f prime of x is greater than 0 when x is bigger than 5. Right? We talked about that. So if x is 6, this will be positive, and this will be positive. So that's our problem. Okay? F then is what? Is increasing for x greater than 5. But we need to show that it is decreasing for bigger than 3, because that's how this is laid out. So it does not work. So the integral test does not apply. Okay, and that's how you set it all up. So that's what you need to check out if you're going to set this up. And so the next example I have down here at the bottom is we're going to look to see whether or not this integral test, the integral test does show that this converges or diverges. Okay? So if you look closely at it, you'll see that this is the exact same example that we had here. Okay? So I don't have to redo all the testing that I had to do over here. Okay? And so I know the integral test does apply, so let's go ahead and do so. All right? And so we let a of n equal f of x, which equals x over x squared plus 1. We have that. Okay? From our previous stuff, we know that the integral test does apply, so we're going to set up our improper integration here. And so we get the integration from 1 to infinity, because remember, we're going to, x is bigger than 1, okay, of x over x squared plus 1 dx. Okay, we're going to infinity because we're going to infinity. And so we have to do this. B is going to infinity, 1 to b of this. Okay, and so we want to integrate this over here, so we're going to do set up our u substitution. So if u is x squared plus 1, then du is 2x dx. Okay, which means 1/2 du is dx, excuse me, x dx. So we can come over here and integrate this now and end up with this problem right here. The integration of it. So this right here, and we have 1/2 the natural log of x squared plus 1, absolute value of that. And we're going to evaluate that from 1 to b. So then we have our limit as b goes to infinity. 1/2 the natural log b squared plus 1. 1/2 the natural log of 2. So this right here, as b goes to infinity, this right here is going to infinity, so this is going to infinity minus the natural log of 2. Okay, so what does that tell me? So that means this thing diverges, and so then I know this diverges by the integral test. And you couldn't see any of that. Okay? So there's that right there. I'll show you my notes over here because I have some side notes I want you to be able to take out. So take a look at those right there. Here's the problem and all the little side notes I did. So show that the integral test can be applied. We showed this in a previous example. Set up the improper integral, which is what we did, and then we worked all this out. Okay? So take a pause here and copy that down. And then I have one more example I want to look at. Okay, so we're going to do this one, use the integral test to determine whether or not this series converges or diverges. So here we go. A sub n f of x 1 over x squared plus 1. Okay, we need to check the criteria. Okay, so we take a look at this thing right here, and you just need to make your statement if it's easy to do. So f of x is positive for x greater than or equal to 1. F of x is continuous for x greater than or equal to 1. There's no place where it's going to be, there's a point of discontinuity, so you're good. And the last one is f decreasing? Okay, So we have to come over here and we do f prime of x equals. So take a look at this and use it as a quantity up to the top, or you can do the quotient rule, whatever you want to do. But literally the derivative comes out to be this right here. And then you can clean this up and you get negative 2x over x squared plus 1 quantity squared. And that is what f of prime of x equals. And so when x is bigger than 1, the bottom will always be positive and the top will always be negative. So I can see that f prime of x is less than 0 for x greater than or equal to 1. So then that's the third criteria. F of x is decreasing for x greater than or equal to 1. So the three criteria have been met, and now we are ready to go. Now, a couple things here. So we're going to set up our improper integration. Because this starts at 1, whatever it starts at, that's your lower limit. So if this thing here started at 3, you would put a 3 here. Okay? And so this right here then is going to infinity, 1 over x squared plus 1. And then we go through this process real quickly. I know you guys know how to do it. And keep on going. This is now the limit as b goes to infinity. And this right here, as you can take a look at here, this right here is the inverse tangent function. Make sure you recognize it from 1 to b. So we keep on going here. So now we have the limit as b goes to infinity, and we'll have the inverse tangent of b minus the inverse tangent of 1. So as b goes to infinity, remember the inverse tangent, if you did not know, I'm going to do a little quick sketch over here. The inverse tangent is defined like so, between negative pi over 2 and pi over 2. So as b goes to infinity, this is getting closer and closer to pi over 2. So that means this is going to be pi over 2 minus pi over 4, which is pi over 4. So since this converges to a value, we can then make our statement 1 to infinity of 1 over x squared plus 1 dx converges. So the sum n equals 1 to infinity of 1 over n squared plus 1 converges by the integral test. And there you go. Okay? Now, I'm going to show you my notes over here so you can copy down the little side pieces that I have written down. And here we go. So here's the setup. Here's all the work we just did. So if you want to pause here and continue copying, you can go ahead and do so. Here's a little note that tells you that this number right here has to match the value that your series starts at. Okay? And then we have a warning. The series does not necessarily converge to pi over 4. Okay? Just because this converges to pi over 4 does not mean that this converges to pi over 4. Do not equate the sum of the series with the value of the improper integral. They are almost always not the same. Okay? So take a pause, finish this off, and if you have any questions, let me know.